All right. Thank you, everyone, for joining the Athena seminar series. Today, we are honored to have Professor Dongsuk Jeon join us. He received a BS degree in electrical engineering from Seoul National University in Seoul, South Korea, and a PhD degree in electrical engineering from University of Michigan. He was a postdoc associate with MIT. And he is currently professor with the Graduate School of Convergence, Science, and Technology at Seoul National University. His current research interests include hardware-oriented machine learning algorithms, hardware accelerators, and low-power circuits. With that, I welcome Dr. Jeon.
Thank you. Thank you for a very nice introduction today. So glad to be here.
Click that OK.
Sorry?
Just click the OK,
okay.
so it
Yeah,
okay. Perfect.
All right, I'm so glad to be here and to be everyone today. So today, in this talk, I'll be discussing how we can come up with a very good hardware solution for, especially for neural network training. So as I will explain later, the neural network training is very different from neural network inference. So if you want to support some kind of training on your chips, then you need to take like different design decisions, and you need to consider many different things. So that's what I'm going to talk about today in the talk. All right, so before going into the details, let me briefly introduce my own lab back at in Seoul National University. So I'm currently working with like around 20 graduate students there, and we named the lab Mobile Multimedia Systems Research Group. The reason was I wanted to design some kind of good hardware platforms or hardware solutions, especially aimed at some mobile platforms. And we want to run some kind of multimedia algorithms on that. So that definitely includes some AI algorithms or some other types of signal processing too. So basically, I'm a chip designer. So starting from my PhD, I have designed so many different, especially digital ICs. But after spending some years in chip design, I realized that, I need to understand actually everything, starting from the algorithm down to system and down to circuits. So that's why I try to hire students with different backgrounds. So in my lab, maybe around like 1/3 of the students are purely working on the algorithm, and the another 1/3 is working on the architecture or SoC designs, and the remaining ones are working on the circuit design, including analog circuits too. So I don't think a single person can do everything from the top to the bottom, but by like collaborating together, I think we can come up with a better solution than the other groups. So currently, we are looking into several topics, especially that includes machine learning processors and low-power digital circuits and some mixed signal circuits for machine learning. And we are also interested in like very basic building blocks for digital ICs like voltage regulator or clocking regulator or something like that. Okay, so today's talk will be about neural network training, and I think all of you in this room are already very familiar with the neural network itself. So we already know the basics of the neural network, right? So it consists of many artificial neurons, which look like the figure on the left side. And essentially, it's taking multiple inputs through some synapses, and each synapse has different its own synaptic weight. So the inputs will be first multiplied by the synaptic weights, and they will be accumulated inside the neuron. And after going through some kind of like nonlinear function, you can generate another output going to the next neuron. So by putting like tons of these neurons together and connecting them together, we can come up with like artificial neural network on the right side. So the reason why I'm explaining this is I want to show you how we can implement or how we can calculate this kind of model on hardware. So how can we actually realize this operation on hardware? So actually, it's very simple. So in computer science or in computer architecture field, people have been using this very simple operation called GMM, general matrix multiply, and it has a form of the equation there. So it's essentially taking two input matrices, A and B, and multiply them together, and multiply once again with another coefficient alpha, and adds beta C to get another output C. So it's very simple and very traditional operation. But somehow we can map the neural network operations onto these type of GMA operations. So let's take a look at a very simple fully connected layer here. So here we need to calculate x1 times W11, x2 times W21, x3 times W31, and actually it's identical to the operation on the right side. So we can simply construct a single raw vector consisting of the input values, and we can also make another weight matrices like that. So by multiplying these two raw vector with the weight matrix, we can easily calculate we can easily realize the fully connected layer. So also, we all know that we usually use batch processing for general model models. So we can just put those raw vectors together to come up with a large input matrix like that. And by multiplying these two matrices, we can get the output as desired. And this is not any different for the convolutional layer as well. So the only difference is how we build this input matrix. So here we need some overlaps because of the convolutional filter pattern. And well, I think you're already very familiar with this into-call operation in PyTorch or any other deep learning frameworks. So essentially, the operation will take the some part of the inputs and construct an input matrix like that. Anyway, so we already saw that this GMA operation is very useful for accelerating or for realizing fully connected or convolutional layers, but that's not the only thing we need. So we also need some other auxiliary operations like activation functions, normalization, and softmax, and some other things. So that means we need actually two different types of computation units or computing circuits on a chip. So, well, actually, it can have like many different names. Well, here I'm calling this deep learning accelerator, but someone can call this GPU or NPU or neural engine, like from Apple. So they can have many different names, but their design essential is very identical. It's pretty much the same. So if you take a look at those the architecture of those chips, they look all like this. All of them look like this. So usually we're gonna have like tons of like computing circuits for accelerating GML operations in one part of the chip, and in another part of the chip we will have vector engine or vector processor to process these other types of the operations too. Also, we're gonna need a large memory, which is usually called on-chip buffer or SRAM, because usually the data we need to process on is huge. So we cannot store everything on a chip because usually the maximum amount of memory we can have is like on the order of megabytes only. So most of the model and input data will be residing in external DRAM, and usually we are gonna take just a chunk of data and temporarily store on this on-chip SRAM, and we're gonna work on that using these two type of circuits. So that's how it works. So it's very simple. So if you look at any kind of chip supporting these AI applications or AI algorithms, they look like this. Then what is the real problem when designing this kind of chip? Well, many people believe that, may think that, oh, we need more computing resources here, but actually that's not the real problem. So if you need higher computing power, then essentially you can just put more computing circuits here. So you can use more multiplier, more adder, whatever arithmetic you need. You can just put some more computing circuits there. Of course, it will increase the chip size, but it's still doable. However, the real problem is in the memory. So the space of the memory is one problem, but the larger problem is the bandwidth. So even if we store everything in the external DRAM, the speed of this like read and write data bus is very limited. So it's usually much slower than the computing circuit itself. So people are always trying to increase the bandwidth, either on this side or on this side too. So that's why state-of-the-art GPUs are using HBM, high bandwidth memory, because it provides much higher bandwidth compared to conventional DRAMs. So it's way more expensive, but it's worth it though. because it can provide much higher bandwidth on that side. And another thing is, even if we take a large chunk onto this SRAM, there's another limited bandwidth here. And it's actually even more difficult to increase the bandwidth inside the chip. So usually when you design this kind of like deep learning accelerators, we need to decide the optimal architecture which can relieve these kind of issues. So we need kind of balancing between the computing power and the available memory bandwidth. So if you take a look at the NVIDIA GPU's architecture, actually it's pretty much simple. You can see that there's like a large memory here, and there's a tensor core, and there's a different type of computing circuits. So actually it can be categorized into two different computing circuits, as I explained earlier. So that the architecture itself is quite simple. Okay, so again, because I'm a chip designer, let's say I want to design a chip supporting some AI application. Then to make a chip, you need to make so many design decisions beforehand, before you actually start designing your chip. Because I'm not sure how many of you have experience with actual chip design, but it's very costly and it takes a lot of time. So usually if you design or fabricate a prototype in maybe 3 nanometer process, it'll cost you like more than, I don't know, $10 million easily. Actually more than 10 million, way more than that, 50 million or something. So if you like spend that much money and later find that, oh, my chip is worthless, or my chip is not good at like accelerating some type of applications, then you're screwed. So that's a real problem. And so okay, so we need to make many different design decisions. And the first design decision is the target platform. So do you want to use your chip for a server in the data center, or do you want to use it for some edge devices? So it'll make a huge difference. So for the data center chips, usually they're much larger and it has much higher computing power. But at the same time, it'll burn a lot of power at the same time. However, for the edge devices, usually the chip must be smaller because the cost matters there. Also, the power consumption should be much lower. So the key for the first platform is usually performance, and the key metric for the edge device is energy efficiency. So they are totally different. Okay, then what about the remaining design decisions? One of the most important thing is that you need to decide whether your chip has to support training or not. So do you want to run some training on your chip or not? So it'll make a huge difference because it'll affect the decision of computation precision and supported DNN models and everything. So that's what I'm gonna talk more about the remaining in the remaining talk. Okay, so we all know that the size of the AI models is increasing very fast, and it's all bit old data. It's like from 3 years ago, but I think the trend is kind of same, right? So we are still seeing that the AI models are increasing kind of exponentially these days, and that means the training cost is actually huge. So I mean, even if you have like 10,000 GPUs, it'll take more than a couple of months to train this model. And time matters, and also money matters, because you're gonna spend, I don't know, maybe tens of $millions just for training a single model. So the training becomes a real bottleneck these days, especially for LLMs or any other huge models. So that's why people are currently looking into the ways of reducing the cost for neural network training. Actually, not the academia, but the people in the industry are more interested in this direction because it'll reduce the cost directly, right? I'll skip this slide here. And also, these days, people are getting more interested in training neural network models on edge devices as well, because they are worried about like privacy and security. So we are not talking about training a large model from scratch. We are just talking about some fine-tuning existing models on edge devices. And in that case, we are going to need some kind of training functionality on the edge device chip too. Okay, so our objective is reducing the cost for neural network training. And maybe you can maybe say that, oh, well, then can you just apply very widely used two techniques, which are quantization and pruning there? Well, they're very, very effective and widely used techniques for the neural network inference. But as I'll explain later, they're not going to work for the neural network training. So that's the biggest problem. Okay, so before discussing about actual issues, let me briefly explain the training process. I think you're already pretty familiar with this, but anyway, let me explain this. So let's talk about let's take the supervised training as an example here. So first, we're gonna initialize the neural network model, and we will start providing some train samples to the model, right? So the train data or train sample will go through the network in the forward direction, and it'll make its own guess. But at the beginning, it's not trained at all, so it's highly likely that the answer will be incorrect, right? So by comparing the output from the network and the ground truth we already have, we can calculate the loss or error, and we can backpropagate this error to update each parameter in the network. So that's how the neural network training is usually done. So after providing like tons of this training data, it'll learn more and more and more, and it'll become more accurate and more accurate later. After that training is done, we're gonna now fix or freeze all the parameters in the network, and we're gonna use the model only for the inference. Now we are providing actual real data which do not have any ground truth, right? So the input data will go through the forward direction, and the neural network model will generate some output, and that's it. So the main difference between these two processes is that the inference step does not have backpropagation or backward propagation. So that's the real difference. And let's take a closer look at the actual operations we're gonna need for the training. So for the forward propagation, we already know what's going on there. So we're gonna take activation and weight and multiply them together and accumulate to get the output. And actually, the type of operations we need for backward propagation is pretty much the same. So during backward propagation, we're gonna need to calculate the error and gradient. And both of the operations can be realized using the same GMM operations here. So then you can come up with this question then. Hey, look, so the type of operation is pretty much the same for the forward and backward propagations. Then why do we have to make a like specialized chip for the neural network training? Because if we already have the inference chip, then can you use the same chip for the training as well? Because anyway, we're gonna need the same type of operation here, right? Skip here. The key problem is that including quantization and pruning, those kind of like lightweight or some cost reduction technique usually does not work at all for the train. So here's an example of the quantization. So I took this experiment from a very old paper. I think it was from Google, published in 2015. So they tried to train a very simple 3-layer model. I think it was 3-layer MLP on MNIST dataset. So it's very easy toy example, right? But even in that case, if you try to reduce the precision down to maybe 14 or 10 bits, actually you're gonna start seeing significant reduction in the accuracy at the end. So here, red line means 14 bits, so might be okay. But if you use 10 bit, you're already seeing some difference there in the error rate. And if you try to use 8-bit, then there's a huge gap. Okay, this is very simple model, trained on a very simple data set. So this training, this performance degradation will be much larger for larger models or more difficult data sets. Then why is it so difficult to quantize the process, quantize the training process? So one of the reasons is that actually the dynamic range you need during training is much larger than the inference. So here, during training, it's kind of feedback. So the result from the previous iteration will affect the result in the next iteration, right? But it's not the case in the inference. So in inference, once you generate the output, then it's not gonna affect the upcoming outputs at all. So that's the real difference. Also, in the early stage of training, the neural network is not trained very well. So it can learn a lot from each training sample. So that means if you look at the amount of or magnitude of parameter update is relatively larger in the early stage of training because it can learn a lot from each sample. However, in the later stage of training, the neural network has been trained pretty well already. So even if you provide a new train sample, the amount of update is usually much smaller. And that's a trend we are looking at in this graph here. So in the epoch 0, it's much larger. The weight update is much larger, but in the epoch 164, it becomes much smaller than that. The problem is you need to represent all these values using a single data format on your chip. So that means you need much higher precision data format for this kind of training process. So as a result, we've seen some papers in the academia on the neural network training processes, but I don't think there's a huge breakthrough until today. So people are trying to reduce the required precision for the neural network training, maybe in the last 10 years. So I think the consensus is probably FP8 might be okay for some easier models, but still for difficult models, we need at least FP60 or even FP32. So that's the situation we are looking at here. Okay, so as a result, if you want to support training on your chip, then you're gonna need much higher precision in your computing circuits, as well as you'll need much larger memory space because each value should be represented using more bits. So you need a larger space and you need much more complicated computing circuits. So here's an example. So we designed a very simple Mac unit, and I think we synthesized the TSMC 40 nanometer process. And the red bar shows the result for the FP32, which is the baseline in this case. And this one shows area, and this one shows the power consumption. And if we can somehow reduce the required precision by 2x, like from FP32 down to FP60, then you can see that area can be reduced by more than 2x, and same for the power consumption too. And if we can go down to FP8, then the saving is much larger. So somehow, if we can successfully reduce the precision for the neural network training, then that means we can make our training processor much more efficient and much cheaper than before. So that was the motivation of our work. So this is our prior work published at ISCC like several years ago. So at that time, people thought that FP8 was not enough at all. And back then, people were still discussing about like ImageNet training, not the LLM or something like that. So they were trying to train some ResNet models or MobileNet or some kind of these vision models on ImageNet. And FP8 was not successful at that time. So we tried to come up with some solution to resolve this problem. So this is what we proposed. So first, we came up with a new data type, data format. Here, essentially, all the values are represented using FP8, AP floating point format, but that was not enough because each dynamic range was too narrow. So that's why we added a shared exponent bias here. So this exponent bias is shared across all the elements in a single tensor. And it was based on the observation that all the values within a single tensor, they look pretty much the same. So the distribution is quite narrow within a tensor. So we thought that, oh, maybe you can use a shared exponent bias here. Of course, the elements that belong to different tensors, they look totally different. So the good thing about this is that we can easily extend the dynamic range, and the cost is just a single additional value. So we only need one AP value, additional value, for the like maybe tens, thousands or 10,000 values in a single tensor. So the cost is quite minimal. Actually, yeah, I have to note that, well, the adding this shared, some kind of shared value was, it was already an existing idea. I think it was first proposed by Intel, but I think we were utilizing this kind of idea in some different ways in this data format. And another good thing is that even if we add this shared exponent bias, the computation itself does not change at all. So let's say we are trying to multiply these two tensors together, then they will have their own shared exponent bias values, right? And they are expressed as these bias terms here. But because we are sharing the same value across all the elements in a tensor, we can take that value out of the summation because it's a shared value. It's kind of constant in this operation. So that means we can perform the tensor multiplication as usual without considering these shared exponent bias values. And only after all the computations are done, we can simply put this back to here. And we know that multiplying by a power of 2 is very simple, right? So it's kind of like addition to the exponent, or it's kind of like shift operation. So it's very efficient. So we verified this data format in the, I think it was in the PyTorch framework, and it worked very well. Okay, so we are so happy, and we thought that, wow, we are done. So we can directly go to the move on to the chip design. So let's make a chip using this data format. Then we can publish a very good paper. But unfortunately, it worked very well in the GPU, but not in the AG. The problem was we didn't actually know that at that time. So the problem is data format itself was fine, but the accumulation precision was very, very important in neural network training. So in GPU, usually the computation circuits in GPU has, they use very high precision for the accumulation. But we did not want to do that in the AGIC processor, because if that's the case, then the size of the accumulator will be much larger than the MAC unit itself. So we wanted to reduce the data precision, but found that, well, it's very critical, and the training performance will be very sensitive to the precision in this accumulator. So we did a very simple example here. Because we are using FP8 data format, maybe natural choice is using the same data format for the accumulator too, right? So if we use just 8-bit data format or 8-bit precision for the accumulation, you can see that even for the Cypher 10 training, the performance will be degraded a lot, and it will simply fail for the ImageNet training. So again, we did lots of simulations and experiments and realized that we're gonna need at least 30 bits for the accumulation. So it's something nobody was talking about. So, well, there was not many AGIC processes for training at that time. So even we didn't know the importance of this accumulator or accumulators precision. So we found that at least 30 bit it was required for reliable training of deep neural network models. Of course, it will increase the power and area. So we saw like 40% power increase, but I think it was worth it because now we can train all the models very reliably. So here's some example experimental results. So if we compare to the baseline FP32 training and live FP16 training, that means we are using FP16 for the accumulation too. You can see that for the Resonant 18 training, all of them just work fine. But if we try to train all the more difficult models like GAN or LSTM, you can see that even FP16 training fails. However, our proposed scheme, which means FP8 data format combined with 30-bit accumulation, was just working fine there, even in those more difficult models. So based on this result, we designed a chip. I'll skip the chip details here. Okay, let me explain this part only. So I think it was pretty much done, but still the overhead of this high precision accumulator was too high. So we wanted to reduce this overhead somehow. And we thought that maybe we can calculate multiple computations in parallel before doing some accumulation. So on the left side, you're looking at the final design here. So essentially, our chip is taking multiple sets of input weight and multiply them together. And before doing actual accumulation, we are combining these partial products first. And only after that, we are adding this kind of intermediate value to the actual accumulation register here. So by doing this, we can reduce the number of access to this accumulation register by a factor of n here. So that's how we reduce the cost or the overhead for the accumulation. And interestingly, it did not only reduce the power consumption, but also improve the accuracy. It's very interesting thing, but actually it makes sense. So again, accumulation matters, and one of the problem is after some training, the value stored in this accumulation register will be increasing further and further. So it will be like this large. However, the value we are trying to add to this accumulated value will be still remaining very small. So it's kind of like adding very small value to a very large value. Because of the limited precision, somehow we will have to truncate the LSPs, some of the LSPs during this addition, right? And again, because the difference in the magnitude of these two values is huge, we're gonna lose a lot of information on the LSP side. However, if we take this architecture, okay, we're gonna combine these partial products first. So that means we are effectively increasing the magnitude of this like temporary value much larger than before. So that's why we are losing much much less amount of information during each addition. And as you can see from this plot, if we try to multiply just two matrices, you can see that conventional architecture has very poor PSNL. But if we try to compute 24 values in parallel, then we can recover all PSNL all the way back to the baseline. So it was very, I think, effective solution for neural network training. Okay, and again, as I said earlier, it also reduces the power consumption by a lot, by like more than 25x or something. Okay, so this is the chip photo, die photo, fabricated in a 40 nanometer LP process. I think it was from TSMC. And this is the test setup. Yeah, this is the packaged chip, our own chip, and we designed our own PCB and hooked it up to a FPGA. And FPGA was kind of interface circuit between the PC and this training processor. And I think this result is the most important result in this paper. You can see that for Resonant 18 training on the ImageNet dataset, the baseline FP32 data format was 69.6%, and we are very close to that. So even so compared to the previous AP training, I think it was from IBM, and it was from KAIST in Korea. So compared to the previous work, we were much closer to the baseline. Also, now we are representing all the values using FP8. That means we can reduce the memory space as well as the required memory bandwidth. So you can see that the amount of external memory access is nearly half of the baseline. Okay, so we designed a follow-up version and published a ESEC in a couple of years ago, but I'll skip this. Also, if you're interested, maybe you can take a look at this later. And we also try to come up with some like in-memory computing solution for neural network training. So we published on a paper at ESEC in 2022, and I think it was kind of the earliest work on the in-memory computing circuit that supports floating point computation, not the fixed point computation here. Okay, I'll skip here. Okay, all right. So we spent like several years designing different types of neural network training processors and in-memory computing circuits. But after spending some years, we found that, wow, it is really difficult. It is really difficult to design these kind of chips because so to design a chip, you need to determine the data format you want to implement on your chip, right? But to come up with the optimal data format, you need to actually train all different type of neural network models to verify if your data format works for training. But well, you're gonna have to do the same thing for the inference, but the difference is for the training, it's much slower. So even for ResNet training, it'll take a couple of days. And for training LLMs, it'll take a month, right? And we are talking about verifying just one single data point. So let's say if you have like 10, maybe not 10, actually, if you have like 100 different data format candidates, then you have to train a single model 100 times. So each cost and time is like, it's kind of nonsense, right? So because of this reason, we wanted to come up with some kind of like more clever solution to determine the optimal data format for the neural network training. So we published another paper at iClear a couple of years ago. So here's the idea. We thought that maybe there might be a way to predict the actual training performance of a given data format without actually training the models. And we thought that maybe we can take a look at the amount of, or the magnitude of errors caused by the quantization of a given data format. Then it can be a pretty good indicator for the performance loss at the end. So that was the basic idea. So we thought that maybe you can take a look at the error magnitude or misalignment angle. So we are comparing the error generated by the given data format to the error generated by the FP32 computation. So here, the good thing about this is that we don't need to train the model all the way from the scratch to like 100 epochs or something. Here, we can simply take a pre-trained model and we can simply provide a couple of training samples. And we can try to calculate the errors using FP32 units and the given data formats. And we can compare these values. So performing this kind of experiment will take a couple of seconds, even for a very large model. So it's very efficient. So so to verify this idea, we try to train 6 different models using more than 200 data formats. So we actually trained those models 200 times using many GPUs at that time, and we found that there is very high correlation between the proposed performance indicator and the actual training performance. So that proves that our performance indicator actually works pretty well. So because using that prediction scheme, we found that we think that the FP134 will be the optimal format for these given 6 different models. And we actually verified it, and we actually trained those models using this data format. And you can see that it achieves the best accuracy compared to the existing low precision training schemes. And you can see that using this FP134, there's virtually zero performance degradation for ResNet 18, and it's pretty similar for ResNet 101, Mobile, Tulare, LSTM, and everything. So it works pretty well for all different kind of neural network models. Okay, I'll skip this here. Okay. All right, so that was the kind of like design framework for the training processes. But starting from a couple of years ago, my students come and talk to me saying that, hey, professor, the training processor is getting larger and larger and larger, and I don't think we can actually fabricate them because it's too costly. and we're gonna need very, very advanced node, CMOS process node, but usually the university does not have access to those kind of advanced node. So that's why we kind of switched the direction of our research a bit. So now, these days, in the last couple of years ago, we are looking into the ways of reducing the neural network training cost on GPUs. So we are not trying to design our own chip, but we are trying to come up with kind of algorithmic solution to reduce the time and cost for neural network training on GPUs. Okay, so let me explain a little bit more about the GPU training. When training a large model on GPU, usually the memory is the bottleneck. So not the memory bandwidth, but the memory space itself is a bottleneck. So even if you have like tens of gigabytes of like on-chip, not on-chip, kind of DRAM on GPU, usually it's not enough at all. Then you may think that that makes sense because usually the model is huge. So the model parameters will be taking up most of the space, but that's not the case for the training usually. So if you look at the breakdown here, the parameter itself is taking a small portion of the memory. The largest portion is taken up by the intermediate tensors. In other words, it's activations. So again, we're gonna generate tons of activations for each layer for the propagation. And we're gonna need these values again during backward propagation, right? So that's why we need to temporarily store the generated activations in the forward propagation stage. And it's taking a large portion of the memory here, right? So we wanted to come up with some solution to reduce this burden somehow. And there's some work, existing work. I think it was also from Google. It's like in this work, so they were simply discarding these activations, most of the activations, and during backward propagation, they are recalculating these activations. So it's kind of a trade-off between the memory space and computational resources here. But still, the memory was the bottleneck. So I think the idea was perfectly fine. So instead, we took a little bit different approach here. So here, instead of like discarding the activations, we thought that maybe we can deeply quantize those activation values, right? And we were not the first one thinking of this idea. In previous papers, some people actually show that we can actually quantize those values up to some extent, maybe down to 2-bit or 3-bit or something like that. And even if you deeply quantize those values, you're gonna see very little performance degradation in the training. And we wanted to push it further. So we wanted to like use maybe 1 bit or maybe lower than that, 0.5 bit precision or something. So it's kind of very interesting activation quantization scheme we came up with in this work. So here, instead of quantizing every single activation into some data format, we are taking a group of activation and we compress this group of activation into a single value. And we quantize this single value once again. So this is how we achieve much lower effective precision. So it can be effectively lower than below 1 bit, right? But the performance degradation will be much higher, right? So we tried several ways of doing this. We show that. So for this group compression, maybe you can take an average value or a median value or a minimum, maximum, or some random selection, right? So those are the options you have, and we saw that in the experiments, taking the group average was the best. And in this paper, I think it was also published in iClear last year. We also theoretically proved that the average is the optimal solution in this approach. So here you can see that on the right side, we compare this with the naive quantization scheme, existing naive quantization schemes. So this test accuracy and the baseline is again FP32 training. So compared to that, if we quantize down to 2 bits of each individual activation, might be okay. But if we quantize all the activations into 1 bit, then the training will simply fail. It will not converge at all. However, if we use the proposed quantization scheme and quantize all the bits down to effectively 1 bit, then actually it's pretty much fine, pretty well. It's training the model pretty well. And even if we go down to like 0.5 bit, it works somehow, right? So here we are not suggesting that we need to quantize or we need to use 0.5 bit accuracy or 0.5 bit precision for all the layers. Usually we're gonna apply this kind of technique only to a subset or some of the layers which are less sensitive to these kind of quantization errors. So this is the alarm framework we suggested. You can see that we first need to calculate the sensitivity of each layer. And for some less sensitive layers, we can apply 0.5 bits. And more sensitive layers, we can apply maybe 4-bit or 8-bit quantization. And you can see that even if we heavily quantize them, and the performance was pretty much the same. So even for the BERT models, the performance degradation was minimal, while we were able to reduce the compress the memory size by more than 10x. So I think it's pretty good trade-off between the storage and the accuracy. So that was the original result we had in the original paper, but reviewers, again, as always, reviewers were asking for more results. So we had to like borrow some very expensive GPUs and did some llama experiment as well. And surprisingly, actually our scheme was working even better on larger models. Maybe I think that makes sense because they are very redundant usually. So they are usually less sensitive to the quantization. Okay, so this year we also published another paper at iClear, and it was another way of compressing the activation, but I think I'll leave it up to you if you're interested. Okay, so I think I only have a couple of more minutes. So before concluding my talk, I want to discuss about a little bit different direction here. So in my talk, I explained to you that why training is really sensitive and training is very difficult to quantize, right? So that's what you know about the deep neural network models. However, interestingly, our brain is working in a totally different way. So if you look at the structure of the human brain, they are consisting of like tons of actual biological neurons connected through biological synapses like this. And it's huge. It has more than 10 to the 11 neurons, and it has more than 10 to the 14 synapses. So it's a huge network. But the interesting thing is that they are exchanging some information as a form of this spike. It's kind of very short electric pulse. But the thing is, if you look at this, actually you can measure this using kind of oscilloscope or whatever you have. If you take a look at the shape or amplitude of this spike, actually they do not change over time much. So it's either there or not. It's kind of 1-bit data, very simple 1-bit on or off data. So that means somehow they're exchanging just 1-bit data, but they are still successfully training this large scale model with very high accuracy, right? So that's something we want to reveal, we want to understand, and that's something we have not done yet. So this type of thing is direction is called neuromorphic computing. So we want to mimic the brain to make our hardware better. Okay, so we also published some like neuromorphic computing algorithms and neurips a couple of years ago, but okay, so I'm not gonna go into the details, but the thing is, currently, the biggest problem is in the neuromorphic computing is that the limited observability. So we need to first see what is going on in our brain, but essentially we do not have such a technology at all. So we can maybe take a look at like 100 neurons simultaneously, but it's very, very small portion of this large network, right? So still we do not understand what is going on in our brain. So you may have seen some neuromorphic computing papers and some neuromorphic computing algorithms, but they are all based on some speculation, based on this very, very limited observed result. So nobody can guarantee that it actually matches what is going on in our brain. Okay, so we also published some like neural processes, but I'll skip those papers. Okay, so let me conclude the talk today. So out there's like so many different types of like machine learning processes, machine learning accelerators with different names, but they're essentially all the same. They are trying to accelerate the neural networks. And again, their architectures will look pretty much the same. The design details will vary, but the architecture itself will be pretty much the same. So for the inference hardware, you may want to you may want to optimize your hardware for running some compressed, very sparse and very low precision models. But if you want a training hardware, then you need much higher precision in your computing circuits on your chip. So again, for designing training processes, we are gonna need higher precision computing circuits. Also, memory bandwidth width is very difficult to solve. So there are some promising solutions. People are still trying to reduce further the required precision for the neural network training, or we can also apply some activation memory reduction techniques that I discussed earlier, or you can maybe look into the neural computing direction too. Okay, so that's all I have today, and thank you very much for your attention.
Questions?
Thank you so much for the talk.
Speak loud.
I had a question on like page 79, 80. So like in the first part of your slides, you said that like having less precision during training, it's hard because like the error will accumulate during training. But for like your second projects, even doing naive quantization to like 2 bits, like it didn't show, like it still holds pretty well to like baseline. And I'm wondering if that's like just because like the models that you are using are like there's so many parameters, but I would assume that even if there are a lot of parameters, wouldn't that mean that like the error should accumulate even more and that will like propagate more to having like a big degradation?
Okay, yeah, that's a very good question, and sorry about the ambiguity in my talk. So actually, those two things are totally different things. So in the first part of my talk, I was discussing about the precision for the computation. So here, we are not reducing the computation precision at all. We are just reducing the precision of the activation value only. We are not deeply quantizing any other values there. Okay. Because again, the motivation was the activation was taking up so much memory space. So we just focused on the part.
So only the
Right.
Oh, okay. Thank you.
Any other questions? And, no questions online. Yeah. How long are you visiting?
How long?
Yeah,
Yeah, for a year.
a year
Yeah.
at Duke. Anything else? Oh,
I was just curious, fairly early on in the talk, you were talking about the memory bandwidths. What are the kind of bandwidths and data rates that we're really looking at these days for the latest training chips and then latest chips that are being used on device?
Okay. I think it will depend on the type of memory you're using. For the data set chips, you're gonna use HBM3 or 4 or something. You're gonna get around tens of gigabytes per second, but it'll be much less on the edge devices, like LPDDR or something.
Thank you.
another question in the back?
Yeah, and our activations and the weights, the same data format, which has MP1, 3, 4.
Oh, sorry, what is this again?
Our activations and the weights are the same data format.
Activation rates, the same data format,
Weights are the
Activation
same
and-
format.
same data format.
Yeah, right. MP1, 3, 4.
Maybe I'm not getting the question very well.
Yeah, I
Sorry.
compare the activation and the weight
Activation weight.
Yeah, wait.
Oh, no. We are not using the same data format for the activation and weight. They are totally different.
Okay. And then what's the data format for activation?
Well, it depends on the work, but in this case, you can see that we are reducing the data format for the activation down to MP1, MP2 or something. But for the weight, I think, I don't recall exactly, but around 8 bit, I think.
The second question is, what's the precision or interface for the intermediate result, such as a partial sum?
In this case, we are using GPU, so it's hard to tell. Even we don't know yet exactly in the GPU what is going on in the GPU because they don't reveal all the details there. But in our training processor ASIC chips, it was again around 30-bit accumulation. So that means the adder itself was actually 30-bit.
And then the third question is, how to determine the scale or the 0 point?
Okay, that's a very good question. I think for training, we decided on the fly. So we tracked the statistics of the samples and we adapted. Yeah, that's I think that's how we did in the process.
Is determine the function.
Yeah, on a chip.
Any other questions? No questions? All right, thank you.
Thank you.